All right, we are on the last section of chapter 4-6. We are looking at applications of exponential functions. So you're going to need a couple formulas for this section. The first formula is A equals PE to the RT. Now, this formula actually is used in a lot of different disciplines, and depending on what class you're in, that will depend on what letters they use. So if you're in marketing, finance, business, they are going to use A and P. And if you're in physics, science, biology, they will probably use N of T equals N naught E to the RT, but they're the same equations, just different letters. Okay, so for our practical example right here, I'm going to use this A and P. So A is going to represent the final amount of whatever you're measuring. P is the initial amount. So in this case, in physics, N of T would be your final amount, N naught would be your initial amount. In science, whenever we put this little subscript of a 0 down there, we say naught. So H naught, N naught, whatever it's below, and it indicates that it's an initial measurement of whatever the letter represents. So that would be the initial amount. R is a rate, and remember that we don't use percentages in math. So this rate has to be a decimal. And T represents time. Now let's take a minute, and the labels on things are really going to help you in this section if you pay attention to them. So labels for amounts, things we're measuring, money, grams of something, pounds of something, the number of animals that we're looking at. We'll look at a lot of different examples. Whatever we're measuring are the labels on the amount. Time, this is going to be labeled in seconds, minutes, hours, years, something like that. And then this rate is going to be a decimal or a percentage. So when you look at a problem, if I look, say, at this first example that we're going to do, and I see that it says $7,000, I don't want to plug that in for T because T is a time and should be measured in minutes, years, etc. Okay. The same is true with this percentage. I don't want to put a percentage in an amount situation. So the labels can really guide you as to what you plug in where. All right, that's the first equation. The second is similar, and we're only going to use the second equation in the context of finance. Every other application is going to be this A equals P e to the RT. But finance also has another option, and it looks like this. And the letters mean the same thing. A is the final amount. P is the initial, stands for principal. Means your start amount. R is still the rate. T is still the time. The N, though, the N represents the number of times your interest, like on a money investment, is compounded, which means, let's see, per year. So, for example, if you're gonna make an investment, and I'm gonna go into your account quarterly and calculate interest to add into your account, then that means N is gonna be 4. Or I might do it monthly, or I might do it daily or yearly. Okay, that's what the N value is. Now, if you get a problem that says that your money is compounded continuously, that means every second of every day, then this is your equation, A equals P e to the RT. So when you have a finance problem, these are your two options, and the way that you tell which one you're going to use is how often interest is being calculated per year. Okay, so for example, let's read our first example. A sum of 5,000 is invested at an interest rate of 8.5% per year. It's compounded semi-annually. That means twice per year. So because it's semi-annually, I am going to use this formula. And I'm going to plug in the values. So a sum of $5,000, that's my initial investment. So that's going to go in for P. The 1 stays 1. An interest rate of 8.5%, that's my R. So I change that to a decimal. That's 0.085. Move the decimal 2 to the left. It's compounded semi-annually. So N is going to be 2. This is also a 2. And then it says, after what period of time? So the question is asking about time, which means T is my unknown. So again, the label is going to help you decide which letter you're solving for. Will the investment amount reach 7,000? So that's going to be my final amount. Okay, and then we're going to solve this equation. So look at what we have here. In the parentheses here, if I plug that value into my calculator, I get 1.0425. You need to not round very heavily in this section or you're going to get into a lot of trouble. If you're going to round something, you need to take it out to at least 4 decimal places. And I would suggest not rounding. So keeping the values on your calculator and using the full decimal as you go. So what we're looking at to solve here for t is an exponential function. So this is what we solved in section 4.5. I've got an exponential. This is my base and my power right there. And so what I'm looking at is a 1 exponent problem. And if you remember our game plan for those, the first thing that we're going to do is isolate the exponent. So now we're going to divide by 5,000. That gets the exponent by itself. So this is going to be 7/5 equals 1.0425 to the 2t, and then you're going to log both sides. Now in this section, we're always going to use a natural log because you can't do a log base 1.0425. And in this section also, we're going decimals. So we're going to just always use the natural log. Natural log both sides. And if you want, you can turn that into a decimal, okay? And 2t comes down in front. So we're looking at natural log of 7/5, 2t natural log of 1.0425. And then you can divide, we're going to get t by itself. So we're going to divide by 2 and the natural log of 1.0425, 2 natural log of 1.0425, and then we go to our calculator. So I'm going to do the natural log of 7/5. And then I'm going to divide that by 2 times the natural log of 1.0425, and I get 4.04. And I go back up to the problem and figure out what my label is. We are measuring in years, okay, per year question. And then, so this is going to be 4.04 years is going to be our time. Okay, so that's how you do that. Now there's a part B to this problem. It says, what if the investment was compounded continuously? Well, if it's compounded continuously, you're going to do the same process, plug in the same values, but this time we're going to be using this formula because this is our compounded continuously formula. So let's take a look at that. We're going to start with A equals P e to the RT. Again, my initial amount is 5,000. My final amount 7,000. E and my rate is 0.085. And we're solving for T. So again, I'm going to isolate my exponential first, divide by 5,000. And the math on these is going to end up looking really familiar after you've done a couple. The math's always the same. Natural log both sides. Now this E and natural log cancel. And so time is going to be the natural log of 7/5 divided by 0.085. So my time is going to be natural log of 7 divided by 5 divided by 0.085. And that ends up being 3.96 years. I don't care if you can round your final answer, just don't round in the middle of the problem. That is what will mess up your answer. So as you can see, the more often your interest is compounded, the faster you earn money, which makes sense. Your interest is earning interest. So if I'm compounded continuously, it's going to take me 3.9 years. And if I'm only interest is only calculated twice a year, it's going to take me 4.04 years. Okay. So that's how you do the finance problems. They're all the same, either the compounded continuously or not. And let's take a look at another type of problem. A gray squirrel population was introduced 3 years ago. Biologists observed the population doubles every 6 years, and now the population is 100,000. What's the population 10 years from now? So when you approach these problems, the finance problems always have an interest rate. Okay, but when you approach any other kind of problem, the first thing you want to ask yourself is, do I know what R is? Do I have a growth rate or a decay rate or some kind of rate of whatever we're measuring? If the answer is no, then it's a two-part problem. The first part is find R, and the second is answer the question with your R value. Okay, so as I read this, I look 3 years is a time, 6 years is a time, 100,000 squirrels, that's an amount. Here's another time. There's no rates in here. So my first step is to find R. 99% of the time, you find R with a sentence that tells you how often the population changes. Okay, so this is our sentence. The population doubles every 6 years. That's always the sentence that helps you find R. Here's how you do it. It's a little trick, and you'll use the same trick for all these problems. What is my initial amount? Well, I don't know. Okay, and that's all right, because I know that after 6 years, so let's put 6 in for our time. R is what we're trying to find. I know after 6 years the population doubles. So whatever this initial amount is, the final amount is twice that. Okay, and that little trick you're going to use on every problem. Well, how does this help me? Well, look at what I can do. As I'm isolating the exponential, I divide through by p first, and it cancels from both sides. So the fact that I don't know my initial population doesn't matter, which is kind of cool and really helpful. And now I can solve this for R. So I'm going to do the natural log of each side. E and natural log cancel. And my R value is going to be the natural log of 2 over 6. Okay, so natural log of 2 divided by 6, that is 0.116. Now, you do not want to, you can round this number by writing it on the paper here, but you do not want to round this number in your calculator. I have a long decimal sitting in front of me. It's 0.11552453001. I want to keep that whole decimal in my calculator and not round that, because I'm now going to use R to answer the question, and you want to use the whole decimal. Okay, so now that's R. Part B, answer the question. Okay, now the population is 100,000. So that's my value now. Okay, it's my initial value, if you will. My R is 0.116, but I have that whole decimal stored in my calculator. And I want to know what is the population 10 years from now? So 10 is a time, goes in here. And I want to know what's my final amount after 10 years. Now, this doesn't have to be solved for anything in the exponent. What I'm trying to calculate is A, so all I have to do is type this in on my calculator. using that whole decimal for R. So if I do that, take E to the R times 10, and I get 317,480. 0.21, but you can't have 0.21 of a squirrel, so we round that to the whole number. So in 10 years, I should have 317,480 squirrels. Now, make sure your answer makes sense. I started with 10,000, now I have 300,000. Yeah, if your value goes down, you probably did something wrong. It should be going up. Population is increasing. So that's how you do these kind of problems. We'll do a couple more of those. This is a similar problem. The only difference is that these problems, the amounts are decreasing. So these are half-life problems. If you've not had a science class where they talk about half-life, the idea is that certain elements decay into different elements over time. So for example, if I have 10 grams of something, after a certain amount of time, I will only have 5 grams of that left. It's decaying and going away. So it's the opposite of a population growth. You're not growing, you're decreasing. But you do the problems the same way. So the first thing I ask myself is, do I have R? And so I read through this problem. I'm talking about radium-226. The half-life, that means the time it takes for it to cut in half, is 1,600 years. Years is a time, so that's not a rate. We have 22 milligrams of a sample. That's an amount, not a rate. And how much will remain after 4,000 years? Again, not a rate. So I don't have R. So the first thing that I need to do is find R. And just like I use the population doubling sentence to find R, in this situation, I use the the amount cutting in half sentence to find R. So the half-life is 1,600 years. So what's my initial amount? I don't know, but I do know that after 1,600 years, I will have half of what I started with. See, it's same trick. But instead of 2p, now it's half p. Divide by p, those go away, and I get 1/2 equals e to the 1,600r. I'm going to natural log both sides. These cancel. Natural log of 1/2 is 1,600r. And r is going to be the natural log of 1/2 divided by 1,600, which is negative 0.000433. 2, 3, 4. Yep. Okay. Now, why is it negative? Well, because the amount is decreasing. So that's a little spot check along the way. If you're doing a half-life problem, your R should always be negative. If you're doing a population growth, it should be positive. All right, now let's answer the question. How much, so it's asking for an amount of the sample, will remain after 4,000 years? Okay, well, how much are we starting with? We have 22 milligrams of a sample. We want to know how much later. My R is what I just found, and my time is 4,000 years. Plug that in. Again, I don't have to solve for anything. I'm just cranking out this number. So 22 times e to the rate times 4,000 is going to be 3.89 milligrams. Okay, again, that makes sense because I started with 22 and I am decreasing, so I have less. All right, another little helpful check along the way. Once you use this half-life statement or the doubling statement, you will never use that again. That is only used here to find R. You will never use those numbers over here to actually answer the question. If that's helpful. Okay, let's do one more. A burial cloth of an Egyptian mummy is estimated to contain 59% of the carbon-14 it contained originally. How long ago was the mummy buried? The half-life of carbon-14 is 5,730 years. So now, this is a little tricky because you might look at this and say, oh, I have a rate because you see the percentage, but it's not a rate. What it's talking about is how much carbon the mummy cloth contains. So this is actually related to an amount. It's an amount of something. It's not the rate, it's disappearing. Okay, so I do not have an R value. So my first step is to find R. And that is always done by using the double or half time. Half-life of carbon is 5,730 years. So I don't know what my initial amount is, but my final is half that, and my time is 5,730 years. Divide through by the P. See how the math starts to really look the same every time. Take the natural log of both sides. So R is going to be the natural log of 1/2 divided by 5,730. And so I get negative 0.00012. That's my R. And now I'm going to answer the question. Now in this problem, what's interesting and different about it is I don't know what the initial amount was. I wasn't around, when it was buried. I don't have any numbers about amounts, but I do have percentages. So we're actually going to use the same trick as before. Here's the initial amount, right? And I've now got 59% of it left. So I've got 0.59 of the original amount. Same kind of trick as we used with the half-life. E is E, the rate is what I found, and the time is the question. How long ago was the mummy buried? This is how they do carbon dating. Divide by the P. So, and I'm going to natural log both sides. These cancel. And so T is going to be the natural log of 0.59 divided by my rate. Remember not to round your rate in your calculator. So I'm going natural log of 0.59 divided by that rate unrounded, and I get 4361.75 years. That's how old the mummy cloth is. All right, there's a worksheet for these homework problems. It is in Canvas. Work that either on the worksheet or on a separate piece of paper and upload that to Canvas. See you next time.